Okay, this is problem number 4 from exam 1. We are given this differential equation up here, and we want to find the method to use to solve this differential equation. If we look at it, we look at all of the different methods that we could possibly use, we might think that homogeneous is the way to go. So maybe just taking a guess at that, we can check to see if homogeneous is the way to go by checking if this equation is homogeneous. To do so, you would just do the substitution, where all of your x's you replace with tx, and all of your y's you replace with ty, and solve. So I have this written down so far. Let's substitute all of our x's and y's in. That'll turn this into tx plus ty. Okay, now looking at all of these different terms, we see that there's a t in all of these terms. So let's first, let me do this real quick just so we know. I messed up there. So why don't we take out a t in every radical. Just factor out a t, really. Okay, and now that we see, this, we can take out a t, we can take the t out of the radical as t to the 1/2 power. So we'll do that, hopefully really quick. 1/2 times x plus y, t to the 1/2 x minus y, t to the 1/2 x minus y, t to the 1/2 x plus y, but in radical. And then we can see that there is a t to the 1/2 in all of these terms. We can factor out a t to the 1/2. And while we do that, or as we do that, I'm also going to subtract this term from both sides of the equation. That might help us simplify it later on. So pulling out a t to the 1/2 out of this term, we will have square root of x minus y minus square root of x plus y, y prime, is equal to, subtracting this this term from the side of the equation, we'll have a negative t to the 1/2, and then x plus y, square root of x plus y, plus square root of x minus y. And then we see that we have a t to the 1/2 power over here and a t to the 1/2 power over here. We can cancel those two out, and we will get, here, I'll write it out, square root of x minus y minus square root of x plus y, y prime, is equal to the negative of x plus y plus x minus y. And we can see that these terms are the same, and it is, and that checks it off as homogeneous. And then, now that we know that it's homogeneous, we can use homogeneous method to solve this differential equation. So I'll move my paper up a little bit. And to the first step for getting to solving homogeneous differential equations is to get y prime by itself. And if we look at the, why don't we go back up real quick, really quick. Looking at our equation again, we can get y prime by itself by subtracting this term from both sides of the equation and then dividing by this side, or dividing by this term. So we'll have y prime is equal to the negative of square root of x plus y minus plus x minus y, and then dividing by this term, we'll have square root of x minus y minus the square root of x plus y. Okay, let me move my paper back down. We have some room. Okay, and then first step in solving a homogeneous differential equation is using substitution. We're going to use the substitution y equals vx. And if you take the y prime, you'll have y prime is equal to v prime x plus v by product rule. So we can substitute our y prime in with this, and we'll get v prime x plus v is equal to, we're going to plug in all of our y's to be vx's. And then at the same time, I'm also going to distribute this negative, just to save us one step. So we'll have a negative square root of x plus vx plus, negative, minus the square root of x minus vx over square root of x minus vx minus square root of x plus vx. Okay, from here we can look at this this big fraction basically as any other fraction, and we want to simplify it. We can have radicals in the denominator, of course. So the way to get radicals out of the denominator is to multiply by its multiplicative inverse. So we will use the multiplicative inverse to simplify. We will have square root of x minus vx plus the opposite sign, square root of x plus vx, and then to make it technically multiplied by 1, we have to have the top and bottom, the numerator and denominator, to be the same. So we are multiplying this this equation by 1, essentially, but it's going to simplify our denominator. And so let's multiply this out. To the numerator first, we will have a negative square root of x plus vx times square root of x minus vx. Those will not simplify, so we're going to have to write it as negative square root of x plus vx times the square root of x minus vx. Looking at the next term, we have x square root of x minus x plus vx and an x plus vx over here. We know that a 1/2 power times a 1/2 power will create a power of 1, making the radicand the answer. So the negative of this times the positive of this will give us the negative of x plus vx, like we said, the radicand. And then doing our next term, we have a once again the radicand will come out. It's going to be the negative, so and then minus x minus vx. Multiplying the last two terms is going to be just like the first two terms again, a negative square root of x minus x minus vx square root of x plus vx. And then we can do our denominator at this point. Multiplying these two terms out, we'll get the radicand. Multiplying the next two terms out, you can see that we have a positive of these two of this product, and then a negative of the same product. Those will cancel out. So we can go to the last two terms. The last two terms will create, once again, we're going to get the radicand as the answer, since x plus vx and x plus vx. It's going to be a negative x plus vx. All right, much more simplified and pretty. We're going to be able to simplify it much more now, and we don't have any radicands in the denominator. I'm going to distribute these negatives just to show exactly what we're doing here, and then distribute this negative as well. So we're just going to rewrite this all as with up-to-date negatives, basically. Minus x minus vx minus x plus vx minus square root. I'm just going to switch these around just to make it more simple to see what we're doing exactly. X minus vx, and then x minus vx minus x minus vx. All right, simplifying this some more. I don't mind move my paper up just so I don't run out of room. We can see that we have the same terms here. So we're going to have a minus this term, we're going to have minus 2 of that term. Okay, let's see, we have an x, negative x, and a negative x. It's going to be negative 2x, and then a vx, a negative vx, and a positive vx that will cancel out. Okay, that's our numerator. Denominator, we have an x and a negative x. Those two will cancel out beautifully. And then a negative vx and a negative vx will have negative 2vx. Okay, now, next step we can do, we're going to combine these two radicals, multiply the radicands, essentially. So we'll have negative 2 square root. If we multiply the radicands, we'll have x squared minus v squared x squared, right? And then, of course, we can close that and negative 2x on the end. And our denominator of negative 2vx. Furthermore, we can pull out an x squared out of this radicand, our factor, negative x squared, or an x squared. So we'll have an x squared 1 minus v squared. Alright, the x squared will come out of the radical as an x, so I'll have negative 2x square root 1 minus v squared, negative 2x, negative 2xv, and just switch those order around so we can see how beautiful this worked out. We have a negative 2x and a negative 2x and a negative 2x, and we will be left with a square root of 1 minus v squared minus 1 all over v. Okay, now let's not forget that we have our v prime x plus v on this side of the equation. I'll just rewrite this for now. Okay, we want to look at this. We can simplify this, subtract a v on both sides, which will give us a v prime x is equal to the square root of 1 minus v squared. And we will have a this will be plus 1. Okay, so subtracting a v, we will have a v squared. I'll have to turn into v squared over v, because v, if we subtract v over 1, we have to multiply it by the denominator, v over v, v squared over v, we can subtract it in. Now, with this, we can get our v prime by itself by dividing by x. So that will turn into v prime is equal to the square root of 1 minus v squared plus 1 minus v squared over v multiplied by 1 over x. And now this is going to be great for us, because if we notice, this is all v's. All the terms in this right here are v's, and all the terms in this right here are x's. And we can look at this almost as a separable variable differential equation now, in a way. If we look at this v prime as being dv over dx. And then, so using that dv over dx, we're going to multiply this side, or technically divide this whole term on this side and this side, giving us v, try and write it tiny, 1 minus v squared, square root of 1 minus v squared plus 1 minus v squared, equals 1 over x, multiply this side by dx, this dx will cancel out dx, and then we can integrate both sides. So I'm going to move this over just a little bit so we can have enough room to play with. Well, we know that, I'll move the equal sign right over here. We know that the integral of 1 over x dx is going to be natural log of x plus c. And we can look at this integration. We can separate the fractions and make it look like 1 over square root of 1 minus v squared minus 1 multiplied by v over 1 minus v squared. And if we look at this, this is the exact same thing as what we have up here. If we multiply the numerators, we'd have a v. If we multiply the denominators, that we'd have 1 minus v squared, because the radicals will cancel out, which is what we have, 1 minus v squared, and then 1 times the square root of 1 minus v squared, right here. So this is the exact same thing as this, but it'll help us when we are trying to integrate it. Solving this, we can do substitution, a u substitution, taking u to be the square root of 1 minus v squared. Finding du, that would be, we can say this is 1 minus v squared to the 1/2 power. That can be 1/2 1 minus v squared to the negative 1/2. Multiplying by the inside of the using chain rule, we would have negative 2v dv. Solving for dv, I like to use when you do use substitution, I like to solve for dx or dv. Dv would then be 1 minus v squared 1/2 over negative v du. These two, the negative 2 and the 1/2 will cancel, and then we would multiply this side, this 1 minus v squared to the negative 1/2, multiply it by 1 minus v squared to the 1/2, and that would go on top of it as in the numerator. Anyways, now we can substitute into our equation, our integral here. That would give us the integral of 1 over u plus 1 times v over, if we look at this, this is our u, okay, we have our u here, and then plugging in for dv, we will have well, if we look at this right here, in the dv is equal to, this is our same as our u, so we can write this as u, and then negative v right here, du. And then we can see that this cancels out beautifully. Negative u's cancel out. We'll bring the negative out here. Okay, now thankfully this is a very simple integration. It's going to be negative natural log of u plus 1, absolute value of u plus 1 is equal to the ln of x plus c. Move my paper up here real quick. We're getting close. Now all we have to do is back substitute our u in, and that will give us negative natural log of the square root of 1 minus v squared plus 1 equals natural log of x plus c. So ignore this box here. I thought this was the solution, but had a realization. We still have a v squared in there. That was a substitution, so we have to back substitute our v in now. If you remember, we did y is equal to vx, meaning that v would be equal to y over x. Now we have to substitute this v back into this equation, giving us the natural log of square root of 1 minus y over x squared plus 1 is equal to the natural log of x plus c. And now this is not our solution. This is our solution. We have our differential equation back in the terms of x and y. And this is the solution, where c is an arbitrary constant.